in this lecture, which will be the fourth lecture of module 6, I will introduce the method of Lagrange's undetermined multipliers, which is a way of finding the extremum, the maxima or minima of functions which satisfy a certain constraint. So, this is a very powerful method, and it is fairly widely used both in quantum mechanics and in statistical mechanics. And what I will show the basics of the method, and then we'll explore certain topics which are related to the foundations of this method. Let us get to the basic task at hand. So, suppose you have a function, we have a function of several variables, and we denote it by, let us say, f of x1, x2 up to xn. Now, we want to find extrema. Extrema means minima or maxima of function of f, okay, subject to a condition. The condition is, we write it in this form, g of x1, x2 up to xn, let us say equal to constant, okay, or I can always take the constant to the left and I can say equal to 0. So, this condition is referred to as a constraint. So, we have this function of several variables and we want to find the extrema of this function subject to this condition. Okay, we will look at examples. I mean, there are the most common examples of these are in basic geometry. You might be asked to find out, a very typical problem is to find the volume of a parallelepiped, find the shape of a parallelepiped that has the largest volume for a given area. Okay, so these are the kind of questions, geometric questions that can be easily answered using this, that are usually of this form. Suppose you want to find it subject to that constraint, okay, then what we notice, so before we give the solution, we notice that x1, x2 up to xn are not independent of each other. Okay, that is because of this condition, okay, there is a relation between all this x1, x2 up to xn. Okay, so they are not completely independent. Okay, so this is something that should be kept at the back of your mind, that these variables are not completely independent. Now, in this case we are treating them as though they were independent, okay, but then we will have to put this constraint. So, now if this constraint was not there, then you would use the expression for total derivative. So, df as dou f by dou x1 dx1 plus dou f by dou x2 dx2 plus dou f by dou xn dxn. This is the total differential of f. The differential change in f is written in this form, okay, and at the extremum this differential change should be 0 because each of these derivatives should go to 0. This goes to 0 at extremum. This is a condition that you have, okay. Now, if you take dg, okay, so the dg, now g is a constant, okay, so dg will also have to be 0, but I can write g also in a similar form. Equal to 0, this is 0 everywhere, okay, this is 0 for all points. So, at all points. What this implies? Now, remember, this is a little strange equation because when you define these partial derivatives, you are keeping all the other variables fixed, okay, but we already said that you cannot do this because all these variables are not independent of each other. Actually, this condition, we use this condition on dg, okay, to this imposes restrictions on dx1 and dx2 up to dxn. For example, you should have dxn is equal to minus 1 over dou g by dou xn times dou g by dou x1 dx1 plus dou g by dou x2 dx2 plus up to dou g by dou x n minus 1 dx n minus 1. This is a so your dx n, for example, cannot be independently varied, it depends on all the dx1 dx2 up to dx n minus 1. Okay, so you cannot independently vary dxn. According to the Lagranges method of undetermined multipliers, okay, so what you do, okay, I won't do the derivation of the method, but what you say is instead of demanding dou f by dou x1 dou x I equal to 0, for all I. So I equal to 1 to n. Okay. So you demand dou f by dou xi minus lambda dou g by dou xi equal to 0. Okay. Now I equal to 1 to n. Lambda is called Lagrange multiplier. Okay. You can clearly see that this should be true, because all we did was we took the second equation here. Okay. So we took this equation, multiplied it by lambda and subtracted it from this equation. Okay. So what we did is basically we did df minus lambda dg equal to 0. So this is basically this condition, and we look at it term by term. Okay, so we looked at it term by term, and I mean there is a formal derivation of this which I am not doing. Okay, but basically this is the basic idea of Lagrange's undetermined multipliers, that what you do is you take the constraint, multiply it by a constant lambda, and now you have n equations. These n equations will help you solve for x1 to xn. Okay, so remember here it looked like you have n equations, but actually the because these dx1 dx2 are not independent of each other, you cannot use that equation in this form. Here in this case when you use this Lagrange's undetermined multiplier, okay, so you have extra variable. So let us now look at an example of how this works. So a very classic example, and this is a typical geometric example. Okay, find the shape of a parallelo with maximum volume given area A. So for a given area A of a parallelepiped, find the shape of parallelepiped with maximum volume. Okay, so what you do is, so just to show you what this problem is, so you have parallelepiped. Okay, parallelepiped has 3 dimensions, so A, B and C. So these are the 3 sides, the length, breadth, width and height. Okay. Now the area A is equal to twice AB plus BC plus CA. Okay. So this is a constraint. Okay. Now volume equal to ABC. This is the function to maximize. When you do this, you will get a relation between A, B and C that will tell you what the shape of the parallelepiped is. So we use the Lagrange's undetermined multiplier. So now the variables are notice that the variables are A, B, C. A, B, C are your variables. Okay, and they are not independent because of this condition. Dou V by dou A minus lambda dou A by dou A, this is equal to 0, implies what is dou V by dou A? Dou V by dou A is B times C minus lambda. Now dou A by dou A has now there are 2 terms with A, so it is twice 2 B plus C equal to 0. This gives you lambda equal to B C over twice B plus C. Take this value of lambda and put it in the next equation, dou V by dou B minus lambda dou A by dou B equal to 0, implies now dou V by dou B, okay, by the same argument this will be AC minus, now lambda is BC over twice B plus C, so this will be twice A plus B, this equal to 0. You can expand this out. So suppose I multiplied by twice B plus C, okay, then I will get 2 ABC and 2 AC square, okay, and I have minus 2 ABC and 2 B square C. So, I can write this as 2 AC square minus 2 B square C equal to 0, AC equal to B square equal to AC. Okay. So, that is the constraint okay, that you get from this second equation. Now, we still have one more equation. Suppose I use dou V by dou C minus lambda times dou A by dou C equal to 0. So, this implies A B minus, now I will again substitute the value of lambda B C over twice B plus C, okay, and I have just one correction. Okay. Dou V by dou B minus lambda times dou A by dou B equal to 0. Okay. So, this implies, now if you take dou V by dou B, you will get A C minus lambda. Now, dou A by dou B, that will give me so let me substitute the value of lambda. So, B C over twice B plus C. Now, dou A by dou B, I can see that twice A plus C, okay, and this has to be equal to 0. And now, if I just multiply out B plus C, okay, so I cancel the 2 and I multiplied the B plus C. So, what I will get is that the first term will be A B C, and here also the first term is A B C, they will cancel, then you will have A C square and you have B C square. So, you have C square times A minus B equal to 0, and C square cannot be 0. So, that implies A equal to B. This is the condition. Okay. We still need to find out C. Okay. So, we will use third equation. So, dou V by dou C minus lambda dou A by dou C equal to 0 implies, now we will have A B minus what you had is B C over twice B plus C into twice A plus B equal to 0, and remember A was equal to B. Go ahead and we do exactly what we did last time. So, what we have A B square and A B C, and you have A B. So, you have A B square minus the term here will be C B square. So, and so equal to 0 implies A equal to C. So, thus A equal to B equal to C. Okay. So, the shape is a cube. So, cube is that shape maximize the volume for a given area. Now, how do we know it is a maximum and not a minimum? If A equal to B equal to C, V equal to A cube. Okay. Now, what about area? Area is basically given by twice A square into 3. So, that is 6 A square. At this point, we do not know whether it is a maximum or minimum volume. Okay. We just know that the volume is extremum. Now, if you want to check whether it is maxima or minima, okay, then you have to take the second derivative. Okay. You have to take the second derivative and look at all those all the constraints that we had used earlier. I can write A is equal to A by 6 under root, okay, and V is equal to A by 6 raised to 3 by 2. Okay. This is a volume that corresponds to an extremum. Okay. And in fact you can verify that this is maximum volume for given area. Okay. You can verify that that you take any other choice for A, B and C, okay, which satisfies this given area, okay, then you will get a lower volume. So, I leave that as an exercise for you. Okay. So, with this I will conclude this discussion on Lagrange's method of undetermined multipliers, okay, and in the next lecture we will work out some practice problems that use the technique of Lagrange's undetermined multipliers, and also use some of the other techniques that we have learnt in this module. Thank you.